Hello everyone and welcome to Fun Physics Problems Part 1. I'm Arav Rastogi and I'm going to be looking at a few interesting and fun physics problems. So if you like that sort of thing and if you're trying to solve some physics problems yourself, this may be helpful. Uh, why don't I jump right into our first problem? It's from the Resnick and Halliday book, The Principles of Physics, and it's edited by Jearl Walker. So it's from the first chapter. It's problem number 11. Suppose that while lying on a beach near the equator watching the sun set over a calm ocean, you start a stopwatch just as the top of the sun disappears. You then stand, elevating your height by h is equal to 1.7 meters, and stop the watch where the top of the sun again disappears. If the elapsed time is t is equal to 11.1 seconds, what is the radius r of the Earth? So why don't we start by breaking down this problem? So we can start by drawing the Earth, just a circle, like so. And for now we can just draw the sun as a point source of light, right? Because when the sun is orbiting the Earth, we can think about it as, for now, as the geocentric model, as the sun orbiting the Earth instead of the Earth orbiting the sun. Now, what we want to find is the radius r of the Earth, right? P1 and P2 represent the different positions of the sun. So this is the earlier position of the sun, and as time goes on, the sun moves from P1 to P2. Now, we consider the first scenario, and since you're at the equator, when the sun is just over the horizon, that's when you can't see it anymore. So we can just draw a line like that while you're lying down. That is your line of sight. And so when the sun moves beyond that, it disappears. So that's the last time you see the sun. Now, when you stand up, you can obviously see farther. And so you can see the sun. I'm just going to exaggerate for effect here. And let's just etch. You can see the sun until it goes to P2. So this line will in fact, this line will actually touch the Earth at some point because it will be tangential to the Earth. That's what prevents you from actually seeing the sun. So we know that this is obviously 90 degrees and this is also 90 degrees. And so using that, we can obtain our first critical piece of information, which is that if we call this angle theta, and this is r, because this is a right angle triangle, the one I'm highlighting in red, we can write that theta is equal to the arc cosine of r over r plus h, because if we look at theta here, this is the adjacent and this is the hypotenuse because it's opposite to the right angle. We can get this by saying that cosine of theta is equal to r, which is the adjacent, over the hypotenuse, which is r plus h. We can also obtain a second piece of information if we think a little more critically about this problem. So let's look at this. This is the distance that the essentially the point where the sun dips, the horizon dips, this is how that point travels, right? And we can just call this di. And so we know that di is equal to, it's just an arc along the edge of the circle. So it's theta by 360 times 2 pi r. And the third piece of information we'll have to get by looking a little more closely at the problem. So we understand that P1 will return to this spot when the sun takes a full rotation around the Earth, right? and that's going to be 24 hours. And so we can then deduce that in 24 hours, the distance traversed will be the circumference of the Earth C. So when d is equal to c, d is equal to 2 pi r, and it is also equal to di times the number of seconds in a day, so that's 24 times 3600 by 11.1. This is because the sun moves di in 11.1 seconds, right, according to the problem. And so in 24 hours, it'll move 24 times 3600, which is the number of seconds in a day, by 11.1. Now we're making a pretty big assumption here, and that is the fact that the rate it moves at is constant. So for example, it doesn't move slowly here and speed up like this. And to be honest, I haven't fully rationalized this, so if someone thinks of a better rationale for this than I have currently, please do mention it in the comments. But I believe that this is because the sun is moving at a constant rate. D should increase at a constant rate as well. So we can now move on and start rearranging this because we actually have all the information we need. We can write that combining this in this equation, we can write 2 pi r is equal to substituting in di theta by 360 times 2 pi r times 24 times 3600 by 11.1. Now these obviously cancel out, and this turns out to be 7783.8 if you just plug that into a calculator. So there we go. And now we can rearrange again. So 360 by 7783.8 is equal to theta, which is just arc cos of r by r plus h, or r plus 1.7, because h is 1.7. And so now we can write cosine of 360 by 7783.8 is equal to r over r plus 1.7. And now we're just doing algebra really. R times cosine of 360 by 7783.8 plus 1.7 cosine 360 by 7783.8 is equal to r. And so r is just equal to 1.7 cosine of 360 by 7783.8 by 1 minus cosine of 360 by 7783.8. And all of this turns out to be 5.2 times 10 to the 6, and our unit is meters because h is in meters. And so this is actually the correct answer given in the answer key of the book, which leads me to believe that this initial assumption that we took here, the di is increasing at a constant rate, is actually correct. If you notice, this is not the actual radius of the Earth. The actual radius of the Earth is 6.378 times 10 to the 6 meters, which is about an 18% error. But considering the very approximate numbers we're working with here, it's honestly not that bad. And because we're considering like an experimental scenario, which is very brief, I think a 20% error is sort of expected. And yes, that's the first physics problem. I think this is quite an interesting one because once you frame it in terms of these equations, and I did struggle with this quite a bit at first because you have to understand how to frame these and which exact equations are relevant and which ones are not. And I was also quite doubtful about the assumption that di increases constantly. But I think in the end, this method seems to work out. If you do find any problems with this method, please write them down in the comments. If you like this video, please mention that in the comments or give a like, because it helps me understand if I can try more of these problems, or if you have any suggestions for different types of problems I might want to try, please do mention that as well. Thank you for watching.